So thus far, we've had the condition that for the Hamiltonian that we deal with conservative forces. And just as we did dealing with the Lagrangian formalism, we're going to introduce non-conservative forces into the Hamiltonian. So we have that the Hamilton's equation, P alpha dot is di H by di Q alpha with the minus sign, yes, with the minus sign. And this is the general equation of motion, and this was derived from our Lagrangian. So d by dt of di L by di Q alpha dot minus di L by di Q alpha equal to 0. And so when that is true, this becomes the equation of motion for the rate of change of the momentum. But we had made the explicit assumption that we were dealing with conservative forces so that we could write L as T minus U. Now, we saw much earlier that the general equation involves the kinetic energy, and then we subtract a generalized force, and this generalized force we could break up into a conservative plus a non-conservative part, and that was equal to 0. And we then absorb the conservative force through a potential into the Lagrangian. And so in that framework, we could still use our Lagrangian defined in the normal way. And we then included these non-conservative forces, usually a friction type force, but any other non-conservative force as another term in the potential. Now we'll use Hamilton's equations in order to rewrite this. And we start by using the definition of the momentum. So our momentum is di L by di Q alpha dot. And then we also have another Hamilton's equations that di H by di Q alpha is minus di L by di Q alpha. And so I have d by dt of P alpha plus di H by di Q alpha minus Q alpha non-conservative is equal to 0. And so we have then a modified equation, P alpha dot is equal to Q alpha non-conservative minus di H by di Q alpha. And then this naturally incorporates a non-conservative force. So now let's look at the time dependence of our Hamiltonian. So we're going to consider dH by dt. And this is equal to, so I should have my summations here. So I will sum over all alpha of di H by di P alpha, no, Q alpha, that's right, and then Q alpha dot, and then di H by di P alpha dot, and then finally a di H by di T. And so we have all of these terms. And if we have no explicit time dependence, so let's assume we will assume that that's equal to 0, and then we can start making substitutions. And there's one more equation that I need. Oh no, I think I have everything I need here. I can start making substitutions. So dH by dQ alpha, I can sub in here. So my total time derivative, dH by dt. And so this is the sum over alpha. And now I make this substitution. So that's Q alpha non-conservative minus a P alpha dot times Q alpha dot plus, and then I have di H by di P alpha, and that's the equation that I was missing. But that quantity is, yes, this is equal to Q alpha dot P alpha dot. That's right. I didn't have this written down anywhere, but that's what the equation of motion is for the velocity. So with these definitions, these two terms cancel, and so the time derivative of the Hamiltonian just becomes a sum over my non-conservative forces times a Q alpha dot. And so if there are no non-conservative forces, then the time derivative of the Hamiltonian is equal to 0. But since we know that the Hamiltonian, in the absence of non-conservative forces, is just the total energy, which must be conserved, that makes sense. If this vanishes, then the time derivative vanishes. Otherwise, we have that the rate of change of the energy in the system is given by our non-conservative forces times the generalized velocity, which is exactly what we would have derived by considering the work in the system.